Welcome to my 20th tutoring session in A-level chemistry. In this video, you'll learn about periodic trends in ionization energy pertaining to group 1-2 and period 2-3 elements. Watch my previous videos on the topic periodic trends in atomic size, effective nuclear charge and shielding effect in group 2 elements. Now these two videos will provide you with a better understanding of this video content. Link to these two videos is given in the description. Please take a moment to watch these videos. In order to understand the concept of ionization energy, one should be familiar with the meaning of core and valence electrons, shielding, and effective nuclear charge. Let me briefly explain these concepts with respect to calcium atom. The nucleus of calcium atom contains 20 positively charged protons and electrons arranged around the nucleus in their respective shells or energy levels. You find 2 electrons in the first shell, 8 electrons in the second shell, and again 8 electrons in the third shell, and only 2 electrons in the outermost shell. I have color coded the core and valence electrons. Core electrons are highlighted in red, while the valence electrons are highlighted in blue. What are valence electrons? Valence electrons are those electrons that are present in the outermost shell, which is also referred to as valence shell. Now these valence electrons are far from the nucleus and easy to remove. Why is that? Why valence electrons are easy to remove? Because valence electrons, they experience a very weak attractive force towards the positively charged protons, and therefore it is easy to remove. Now what about the core electrons? Now core electrons are those electrons that are present in the inner shells. Core electrons are closer to the nucleus and difficult to remove. So why it is difficult to remove the core electrons? Because the core electrons present in the inner shells experience a strong attractive force towards the positively charged protons, and therefore it is difficult to remove. And core electrons are also called as shielding electrons because they contribute to shielding. Now, what is shielding? Now, shielding is a phenomenon where the inner core electrons partially block or reduce the electrostatic force of attraction between the positively charged protons and the valence electrons. And most importantly, the core electrons reduce the effective nuclear charge. So what is the effective nuclear charge? It is the electrostatic force of attraction between the positively charged protons and the outermost electrons. So usually it is referred to the valence electrons. So effective nuclear charge can also be defined as the net positive charge experienced by the electrons in a multi-electron atom. Now each new energy level or shell with core electrons adds more shielding between the outer valence electrons and the nuclear protons, and this will lead to weaker attraction between them, and as a result of shielding, the valence electrons can be easily removed. So lesser the shielding, more easily the valence electrons can be removed. More the shielding, difficult it will be to remove the valence electrons. And when the effective nuclear charge is more, it will be difficult to remove the valence electrons. There are some more terminologies one should know before going into the details of periodic trends in ionization energy. So you should be familiar with the meaning of ions, ionization and ionization energy. So what are ions? Now, ions are electrically charged particles that result from the gain or loss of one or more electrons by an atom. So ions can be either positively charged called cations or negatively charged called anions. So let me explain this, the example of formation of the common salt sodium chloride. Now the sodium loses its outermost valence electron to chlorine, and that results in formation of sodium ion and chloride ion. So what is the driving force for the formation of the common salt sodium chloride? Now the electronic configuration of sodium is 281, and after losing the only valence electron, it attains the stable electronic configuration of neon, which is the nearest noble gas in the periodic table. And chlorine with electronic configuration of 287, after gaining the electron given by the sodium atom, it attains the stable electronic configuration of argon, that is 288. Now the pros of formation of ions, like for example formation of sodium ion and chloride ion, is called ionization. So ions are formed when atoms undergo a process called ionization, which involves the gain or loss of electrons. So here in the case of sodium chloride formation, you can see both gain of electron as well as loss of electrons. So gain of electron by chlorine and loss of electron by sodium. And what is ionization energy? Ionization energy is the amount of energy required to remove the electron from an isolated gaseous atom or ion. So let me explain this with the help of lithium atom. Now when lithium undergoes ionization, it loses its outermost valence electron, and that results in the formation of lithium ion. So ionization energy is the amount of energy required to remove an electron from an atom or ion in its gaseous state, and it's the measure of strength of the attraction between the electrons and the atom's nucleus. So the amount of energy required to remove the valence electron from the lithium atom is plus 520 kilojoules per mole of energy. So 520 kilojoules per mole of energy is required to remove the valence electron from lithium atom. So it is an energy demanding process. So why is that? Why ionization is an endothermic process and energy demanding process? Because of the Coulombic force of attraction between the positively charged protons present in the lithium atom and the valence electron present in the outermost shell. So in the lithium you find 3 protons in the nucleus, which attracts the electron present in the outermost shell. So it tends to hold that valence electron because of the Coulombic force of attraction. So you need to overcome this electrostatic force of attraction in order to remove the valence electron, and therefore it is a energy demanding and endothermic process. So remember, ionization is always an endothermic process because of the electrostatic force of attraction between the nuclear protons and the valence electrons. And ionization energy is usually expressed in units of kilojoules per mole or electron volts. Now let me walk you through some of the important factors affecting the ionization energy, like atomic radius, which is inversely proportional to the ionization energy, electron shielding or shielding effect, also known as screening effect, is inversely proportional to the ionization energy, nuclear charge, which is directly proportional to the ionization energy, electronic configuration of the atom, and the penetration effect. So let me start with the explanation about the atomic radius affecting the ionization energy, and explain this with the help of group 2 elements beryllium, magnesium and calcium. So in case of beryllium, there are 4 protons in the nucleus, 2 core electrons in the first shell, and 2 valence electrons in the outermost shell. Atomic number is 4 with 4 protons. Electronic configuration is 1s2, 2s2. Magnesium has 12 protons in its nucleus, 2 core electrons in the first shell, 8 core electrons in the second shell, and 2 valence electrons in the outermost shell. Atomic number is 12. That is, it contains 12 protons in its nucleus. Electronic configuration is 1s2, 2s2, 2p6, 3s2. Now I have color coded the electrons as I already mentioned. So stick to this color code till the end of my session. So valence electrons always will be highlighted in blue, while the core electrons will be highlighted in red. Even the same will be reflected in the electronic configuration. So in case of calcium, contains 20 protons in its nucleus, 2 electrons in its first shell, 8 electrons in the second shell, again 8 electrons in the third shell, and 2 valence electrons in the outermost shell. Atomic number is 20. Now as the number of shells increase, so when you go down the group from beryllium to calcium, you can see that the number of shells increase. So what happens when the number of shells increase? When the number of shells increase, the distance between the positively charged protons in the nucleus and the valence electron also increases. So in case of beryllium, the atomic radius is 110 picometers. In case of magnesium, atomic radius is 140 picometers. Well, in case of calcium, atomic radius is 175 picometers. So as the distance between the nucleus and the outermost valence shell increases, there is decrease in the attraction between the positively charged protons in the nucleus and the outermost valence electron. That is to say, as the number of shells increase, the size increases, and as a result, the outermost valence shells are loosely held. In case of calcium, well, in case of beryllium and magnesium, in comparison to calcium, the valence electrons are a bit tightly held. So in case of calcium, the valence electrons can be easily removed. Why? Because they are loosely held because of the distance from the nucleus. So atomic radius will be inversely proportional to the ionization energy. So when the atomic radius increases, ionization energy decreases. So in case of calcium atom, so atomic radius increases, and what about the ionization energy? So less amount of energy is required to remove the valence electrons in case of calcium atom. Therefore, atomic radius is inversely proportional to the ionization energy. And as the number of shells increase, the electrons increase, and this leads to increase in the electron-electron repulsion, and the atomic size increases as the electron cloud expands, as the electrons will be occupying more space. Now coming to the second factor, electron shielding. It's also called as shielding effect or screening effect. So already I have explained the meaning of shielding. So what is shielding? Now shielding is a phenomenon where the inner core electrons partially block or reduce the electrostatic force of attraction between the positively charged protons and the valence electrons. So each shell with core electron acts as a shield. So in case of beryllium, you find one shell with 2 core electrons. In case of magnesium, you find 2 shells with core electrons. That is, in magnesium there are a total of 10 electrons. 2 electrons in the first shell and 8 core electrons in the second shell. So in case of calcium, you find 3 shells with core electrons. First shell with 2 core electrons. Second and third shells with 8 core electrons each. So as the number of shells increase, the core electrons also increase, and this leads to shielding. So each shell acts as a shield, and as the number of shells increase, the shielding also increases, and as a result, the attraction between the positively charged protons and the outermost valence electrons also decrease. So as the shielding increase, it will be easier to remove the valence electrons because of the decreased attraction due to shielding or screening effect. And therefore, shielding effect or screening effect will be inversely proportional to the ionization energy. So as the shielding effect increases, ionization energy decreases. So in case of beryllium, less shielding and therefore ionization energy will be more because the electrostatic force of attraction will be more because of less shielding and therefore more energy will be required. While in case of calcium atom, shielding is more with more number of shells with core electrons, and as a result ionization energy decreases. So you can easily remove the valence electrons in case of calcium because of shielding effect, increase in shielding effect, while it will be difficult to remove the valence electrons in case of beryllium because of less shielding. So less energy will be required in case of calcium and more energy will be required in case of beryllium because of shielding effect. So shielding effect will be inversely proportional to the ionization energy. Shielding effect increases, ionization energy decreases. So moving on to the next interesting factor, that is nuclear charge, which is directly proportional to the ionization energy. Now to understand the nuclear charge factor affecting the ionization energy, so you need to understand the periodic trends in size in the periodic table as you move from left to the right side. Now as you move from left to the right side in the periodic table, you'll see that the atomic size decreases. When you move from left to right, starting from lithium, followed by beryllium, boron, carbon, nitrogen, oxygen and fluorine, you can see the atomic size decreases. And observe very closely the number of protons present in the nucleus of these atoms. There are 3 protons in case of lithium, 4 in case of beryllium, 5 in case of boron, 6 in case of carbon, 7 protons in case of nitrogen, 8 protons in case of oxygen, and 9 protons in case of fluorine atom. So there are 2 important things you need to take into consideration. One is the number of shells and the number of protons. As you move from left to the right in the periodic table, you'll see that the number of protons increase. So as the number of protons increase, the Coulombic force of attraction also increases, and therefore the effective nuclear charge also increases. But what about the number of shells? Number of shells remain constant. That is, you find only 2 shells in case of all this 7 atoms. So number of shells constant, only 2, and therefore shielding is constant. So as you move from left to right in the periodic table, shielding is constant, whereas the number of protons increase, the Z effective increases. So let me simplify this explanation comparing the size of lithium atom with fluorine atom. So in case of lithium atom, you find 3 protons in the nucleus, and because of Coulombic force, it attracts the outermost valence electron closer to the nucleus. Now let's see what's the scenario in case of fluorine atom. In fluorine atom, there are 9 positively charged protons, and you can see that the valence electron is pulled very closer to the nucleus because of the magnitude of positive charge. There are a total of 9 protons in case of fluorine as compared to 3 protons in case of lithium atom. So because of the magnitude of positive charge is more in case of fluorine, it pulls the electrons closer to the nucleus and size of the atom decreases. So it is a logic reasoning that it will be very difficult to remove the electrons from fluorine because of the magnitude of the positive charge. But it will be easier to remove the electrons in case of lithium atom because the magnitude of positive charge is less. So it is the magnitude of positive charge which dictates or governs the ionization energy. And therefore, you can conclude that nuclear charge is directly proportional to the ionization energy. As the number of nuclear protons increase, the ionization energy also increases. As the nuclear charge decreases, ionization energy also decreases. Moving on to the next factor, electronic configuration. Now, atom with partially filled orbitals are always unstable. Like in case of the oxygen, we'll find that the electron configuration is unstable, or you can say unstable electronic configuration of oxygen is because of partially filled orbitals. So always the partially filled orbitals, atoms with partially filled orbitals will be unstable. So what about half filled orbitals? Atoms with half filled orbitals will always be stable. Like for example, you can see the stable half filled electronic configuration of nitrogen. It is 1s2, 2s2, 2p3. So the p orbital contains 3 electrons, 1 electron in each 2p orbital. So general formula will be ns2, np3. So atoms with this general formula ns2, np3 will always be stable because of their half filled electronic configuration. And even the atoms with the fully filled electronic configuration will also be stable. Like in case of helium, the 1s orbital is completely filled with 2 electrons. And even in case of neon, you can see that the 2p orbital is completely filled. So electronic configuration of neon is 1s2, 2s2, 2p6. So you can find the stable electronic configuration in case of neon, which is a noble gas. So that is why noble gas, you can find the noble gas elements in the periodic table, the last group, the 0 group. And they are always stable because of their completely filled orbitals. And this fully filled orbitals in the outermost shell contributes to the stability of the inert gases. So always remember, half filled and fully filled orbitals, or the atoms with half filled and fully filled orbitals, will be always stable, while the atoms with partially filled orbitals will be unstable. So bear these 2 points in mind when I take up the practice questions. These 2 points will be taken into consideration. And the last and important effect, I mean the factor, that is penetration effect. So what is penetration effect? Now electrons in the orbital that are closer to the nucleus experience a strong attractive force towards the nucleus. So electrons in orbitals or that is closer to the nucleus will always experience a strong attractive force. Like for example, electrons in the 1s orbital and 2s orbital, they are very closer to the nucleus, and therefore they will experience very strong attractive force, and therefore it will be very difficult to remove these core electrons. While the electrons which are in a higher energy level can be easily removed because of their weaker attractive force towards the nucleus. So core electrons that are closer to the nucleus experience a stronger attractive force, therefore difficult to remove. That is to say, they can penetrate better. They will be attracted more towards the nucleus, positively charged nucleus, as compared to those orbitals which are far away. Now, valence electrons are far from the nucleus and they will experience a weaker attractive force, and therefore it will be easier to remove the valence electrons. So, penetration refers to the closeness of an electron in an orbital to the nucleus of an atom. So, closer the orbital to the nucleus, penetration effect will be more. For example, electrons in the 1s orbital that are closer to the nucleus than those in the 2p, 3s and 3p orbitals will be always easier to remove the electrons. So, it will be always easier to remove the valence electrons than the core electrons because of the penetration effect. So, penetration in general, it refers to the closeness of an electron in an orbital to the nucleus of an atom. Closer the orbital to the nucleus, difficult it is to remove the electrons from these orbitals. So, these are some of the important factors affecting the ionization energy. Now, let's take up the periodic trends in ionization energy. Now, ionization energy increases across a period as you move from the left to the right in the periodic table, and it decreases down a group. So, we will take up elements from group 1, group 2, as well as elements from period 2 and period 3, and study the scenarios relating to the ionization trends in the periodic table. First, let me discuss the ionization energy trend of group 1 elements. I picked 3 elements for explanation: lithium, sodium and potassium. So, lithium, sodium, potassium are group 1 elements with only one valence electron in its outermost shell. When lithium undergoes ionization, it loses its outermost valence electron, forms a lithium ion, and 520 kilojoules per mole of energy is required to remove the outermost valence electron. While in case of sodium, it undergoes ionization, loses its outermost valence electron, changes into a sodium ion, and 513 kilojoules per mole of energy is required to remove this valence electron from the sodium atom. And when potassium undergoes ionization, potassium loses its outermost valence electron, changes to a potassium ion, and 419 kilojoules per mole of energy is required to remove the valence electron from potassium. So, when you compare and contrast these 3 ionization energy values, what do you learn, or what can we conclude? So, as you go down the group, you can see the ionization energy value is decreasing. It is decreased from 520 to 419. So, 520 in case of lithium, 513 in case of sodium, and 419 in case of potassium. You can see a gradual decrease in the ionization energy. Why this particular trend or pattern that you observe? These are the reasons. So, as you go down the group, shells increase, and as a result, the size of the atom increases. As a result of the increase in the size of the atom, the distance between the nucleus and the valence electrons increase, and as a result, shielding increases, and attraction between the valence electrons and the positively charged protons in the nucleus also decrease. As a result, effective nuclear charge decreases, and end result is it will be easier to remove the valence electrons. And when it is easier to remove the valence electrons, what about the ionization energy? The ionization energy goes down. So that was one part of the discussion that was related only to the valence electrons in group 1 elements. Now, let us see what happens when we remove the core electrons from the group 1 elements. The electronic configuration of lithium is 1s2s1. Lithium loses its only valence electron, and 520 kilojoules per mole of energy is required. Sodium loses its only valence electron. 513 kilojoules per mole of energy is required. Potassium loses its only valence electron. 420 kilojoules per mole of energy is required. So this is what we have discussed and understood so far, and why the energy decreases down the group from lithium to potassium. But let's see what happens when we try to remove the core electrons. So let's see what happens when you remove the core electrons from the lithium atom. So this will be the second ionization energy. So first ionization energy is the energy required to remove the first electron, and second ionization energy will be the ionization energy required to remove the second electron, so on and so forth. So you can see that the energy required to remove the core electron is 7,300 kilojoules per mole of energy. You can see a jump, 14 times jump in the ionization energy. That is because we are removing a core electron that is very close to the nucleus. As I already explained, core electrons, this is because of the penetration effect. Now core electrons are those electrons present in inner shells which are very closer to the nucleus. It experiences a very strong attractive force towards the protons, and therefore more energy has to be spent. You have to spend more energy now to remove the core electrons. So what about the sodium atom? When you try and remove the core electron from the sodium atom, that is when it undergoes second ionization energy, second ionization, 4,560 kilojoules per mole of energy is required. So you can see a 9 times jump. And what about potassium? When we remove a core electron from the potassium, that is when it undergoes the second ionization, 3050 kilojoules per mole of energy is required. So you can see a 7 times jump. So there is no jump in, you don't see a large amount of energy being required to remove the valence electron. While coming to the core electrons, there is a immediate jump in the energy required. So always the first ionization energy involving the valence electrons will be always less. And second ionization energy, if it is involving the core electrons, it will be more. And what is the takeaway from this discussion so far pertaining to group 1 elements undergoing ionization, first and second ionization? So there will be no jump in ionization energy with valence electrons, while you see there is a jump in the ionization energy with the core electrons. So you see a 14 times jump in case of lithium, 9 times jump in case of sodium, and 7 times jump in case of potassium. So again, you can see as you come down the group, again the increase in the energy is also reducing because of the size, atomic size, shielding, effective nuclear charge, penetration effect. So all these factors will be taken into consideration. Now coming to the group 2 element, I picked the magnesium element to explain the ionization concept. Electron configuration of magnesium is 1s2, 2s2, 2p6, 3s2. So magnesium has 2 valence electrons. So first ionization energy is the energy required to remove the first valence electron, while the second ionization energy is the energy required to remove the second electron. And let's see what happens when we remove the first valence electron. So when you remove the first electron, it undergoes ionization, first ionization, and 738 kilojoules per mole of energy is required. So what is left over now? One more valence electron is left over. Let's try and remove that. Let's see what happens. So when you try and remove the second valence electron, what is the energy required? 1500 kilojoules per mole of energy is required. So this is the amount of energy required to remove the second valence electron. Now let's go one step further and try and remove the core electron and see what happens. So when I try to remove the core electron, you can see the amount of energy required is much more. Nearly 8000 kilojoules per mole of energy is required. So you can see a 4 times jump. So there is no jump in ionization energy when the valence electrons are removed, but there is a jump in the ionization energy after the removal of 2 valence electrons. That is, when you remove the valence electrons, there is no change in ionization energies. There is change, but not, but there is no drastic change. But when you remove the core electrons, you can see a drastic change. So after 2 valence electrons are removed in case of magnesium, it will attain the stable electron configuration of neon, and that is one more reason why there is jump. So once 2 valence electrons are removed, it will attain the stable electronic configuration of neon, and once the stable electronic configuration of neon is attained, which is the nearest noble gas in the periodic table, it will be difficult to remove. It's not that it is impossible, it is difficult to remove. So more energy is required. So first ionization energy refers to the energy required to remove the most loosely held electron. So these valence electrons are loosely held as compared to the core electrons. So electronic configuration of magnesium is 1s2, 2s2, 2p6, 3s2. There are 2 core electrons in the 1s orbital in the first shell. Again, 2 core electrons in the 2s orbital, and a total of 6 electrons in the 2p orbital, and you find a total of 8 electrons in the second shell, and you find 2 electrons in the 3s orbital, that is in the third shell. So you find 2 valence electrons in case of magnesium, and the electrons in the 1s orbital that are closer to the nucleus will experience a strong attractive force as compared to other orbitals which are at a higher energy level. So electrons in the orbitals that are closer to the nucleus will be difficult to remove because of the penetration effect as compared to the valence electrons that are present in orbitals at a higher energy level. So there is no jump in the ionization energy when the 2 valence electrons in the third energy level are removed, but there is jump in the ionization energy after the removal of the core electron, because the core electrons, they are closer to the nucleus. So it's because of the penetration effect. So there is a jump in the ionization energy after the removal of the core electron, because the core electrons are removed that are closer to the nucleus. So always more energy is required to remove the core electrons as compared to the valence electrons, because the core electrons are very closer to the nucleus. Now moving on to the ionization energy trend in period 2 elements. Now which atom has the highest ionization energy? Nitrogen or oxygen, beryllium or boron? Now when you observe the period 2 elements, if you go by the trend, they should be, or the ionization energy increases across a period. So ionization energy increases across a period as you move from left to the right side of the periodic table. But there are some exceptions. There are few exceptions to this general trend in the periodic table across a period, and this exceptional behaviors will be the most repeated questions in the examinations. The examinations, as the difficulty level increases, questions will be asked pertaining to the exceptional behaviors of elements in the periodic table. So you can see the energy has to increase as per the general trend. The ionization energy has to increase from left to right, but you can see that beryllium is 900 as compared to boron with 800 kilojoules per mole of energy. So this is pertaining to the first ionization energy. So why is that? Let's see. And even in case of nitrogen and oxygen, so oxygen has to be more, energy has to be more, but it is the other way around. So nitrogen, you require more energy as compared to oxygen. So it is going against the trend. So remember these two exceptional cases in case of ionization energy across the period pertaining to beryllium, boron and nitrogen, oxygen. Now in case of nitrogen, electronic configuration is 1s2, 2s2, 2p3. Now this electronic configuration is stable. This electronic configuration of nitrogen is highly stable because the orbitals are half filled. As I have already mentioned, half filled orbitals are always stable. I mean the 2p orbitals. Now the 2p orbitals in case of nitrogen is half filled, and that leads to the stable electronic configuration of nitrogen. And what about oxygen? Now the electronic configuration of oxygen is highly unstable because of partially filled p orbital. So in case of nitrogen, 1400 kilojoules per mole of energy is required to remove the valence electron, that is p electron. Well, in case of oxygen, 1300 kilojoules per mole of energy is required. So why the difference? Because nitrogen it already has a stable electronic configuration. So in order to overcome this stable electronic configuration, more energy has to be supplied, or it is an energy demanding process because of the stable electronic configuration. But it's the other way around in case of oxygen. In oxygen, you find a total of 4 electrons in the 2p orbital, and you find the first p orbital, it is having 2 electrons, while the other 2 orbitals are having 1 electron each. Now, when you are dealing with ionization energies, you need to look at what happens after removal of an electron. So here, after removal of 1 electron, in case of oxygen, it leads to a stable electronic configuration. So after you remove 1 electron from the 2p orbital, where you find the paired electron, this removal of 1 electron leads to stable electronic configuration resembling that of nitrogen. So always when you are dealing with ionization energy, always look what happens after removal of electron. So after removal of 1 electron, in case of oxygen, it leads to a stable electronic configuration. And that is why less energy is required in case of oxygen. While in case of nitrogen, it already has a stable half-filled electronic configuration, and therefore more energy has to be supplied, or it is an energy demanding process. Now coming to beryllium and boron. So beryllium has a stable electronic configuration of 1s2, 2s2 with both 1s and 2s orbitals completely filled with electrons. Whereas in case of boron, it has an unstable electronic configuration. Where you find the 2p orbital is partially filled. And remember, the key points what I mentioned before, always the partially filled orbitals will be unstable as compared to the half filled and fully filled orbitals. Now half filled and fully filled orbitals will always be stable as compared to partially filled orbitals. So in case of beryllium, it has a stable electronic configuration with a filled shell. So energy required less energy amount of energy is required in case of boron as compared to beryllium, because I told you when you're dealing with ionization energies, you need to take a look at what happens when you remove, or what happens after removal of an electron. So after removal of an electron, in case of boron, it gains a stable electronic configuration and therefore less energy is required. While in case of beryllium, more energy is required. Why? Because it already has a stable electronic configuration. So you have to disrupt the stable electronic configuration of beryllium. Therefore, more energy is required. So 900 to 800. So 900 kilojoules per mole of energy is required in case of beryllium as compared to 800 kilojoules per mole of energy in case of boron. Now some more practice questions relating to the periodic trends in ionization energy. Now which atom has the highest energy? Ionization energy. Now moving on to the period 3 elements. So beryllium, boron, nitrogen, oxygen, they were period 2 elements. Now let's take up some elements belonging to period 3. So which atom has highest ionization energy? Magnesium or aluminum? Now going with the trend, ionization energy increases across a period and decreases down a group. Now magnesium, it has a stable electronic configuration with all its orbitals completely filled. So always focus your attention on the outermost shell, because it is the outermost shell from where the electrons are being removed. So in case of magnesium, the outermost shell will be the third shell, and here the third shell, that is the 3s orbital, is completely filled with electrons, and therefore it gives a stable electronic configuration. As compared to aluminium, it has a unstable electronic configuration. Why? Because its outermost 3p orbital is partially filled, or the third shell electrons. Now the 3p subshell is in a higher energy level than the 3s subshell. Now there are alternative ways of approaching to the ionization energy trends in the periodic table. So first, let us take a look at from the point of electronic configuration. So stable electronic configuration in case of magnesium and unstable electronic configuration in case of aluminium, because one of the orbital is p orbital is partially filled. So you find unstable electronic configuration in case of aluminium because the p orbital is partially filled. So that is one way of explaining the ionization energy trend. The other way of approaching is that in terms of energy levels, you can see that the 3p orbitals, they are at a high energy level as compared to the 3s orbital in case of magnesium, and that is why it is easier to remove an electron in case of aluminium as compared to magnesium. So 740 kilojoules per mole of energy is required in case of magnesium as compared to only 575 kilojoules per mole of energy in case of aluminium. So in case of magnesium, it is completely filled, stable electronic configuration with this 3s subshell completely filled, and they are closer to the nucleus as compared to the electrons in the valence electrons in the aluminium. So what about aluminium? So in case of aluminium, you see partially filled 3p subshell, and it is far from the nucleus. So since it is far from the nucleus, since it is at a high energy level, it is easy to remove. And another alternative way of approaching is in terms of electronic configuration. So after removal of 3p electron, I told you, when you're dealing with ionization energies, you need to take a look at what happens after removal of an electron. So removal of 3p electron gives a stable configuration in case of aluminium. Now, which atom has the highest energy? Phosphorus or sulfur? So again, period 3 elements. Let's take a look at the electronic configuration first. Now, phosphorus has a stable electronic configuration 1s2, 2s2, 2p6, 3s2, 3p3. I told you in the beginning of my session, atoms with the general electronic configuration of ns2, np3 will be highly stable because they have half-filled stable electronic configuration. So when you observe the valence shell, the third shell electrons, the 3p subshell is half-filled and highly stable. It has got a stable half-filled configuration and therefore difficult to remove with a ionization energy. Now in case of sulfur electronic configuration, it has a unstable electronic configuration with partially filled orbitals, that is 3p orbital. So the third shell contains a total of 4 electrons. The 3p orbital in case of sulfur contains total of 4 electrons, and in the first p orbital electrons are paired, while the other two p orbitals you find 1 electron each, unpaired electrons. So you find pairing of electrons in the first p orbital in case of sulfur, and as a result this leads to increased electron-electron repulsion, and removing an electron gives a stable half-filled electronic configuration, and therefore end result will be, it will be easier to remove with a lower ionization energy, and only 1000 kilojoules per mole of energy is required in case of sulfur as compared to 1012 in case of phosphorus. Don't forget to subscribe my channel, share and like my videos. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.